Okay, good morning, guys. Today we just want to, where is that? Okay, so we just want to revise question 2 and question 3 of Math 2300 test 1. Okay, so this is real analysis. So we want to revise question 2 and question 3. Okay, so let's get into it. Okay, so question 2 is here. And the first question there, they're saying, define the following terms, okay? There's a one-to-one relation and there's an on-to relation, okay? So let's start from there. Okay, so this is question 2. So the first one there, they're saying define a one-to-one relation, and then they're also telling us to define what an on-to relation is, okay? So before you define, you may want to write a mapping, okay? So we'll say let the relation R be a mapping from set X to set Y, okay? And then if you can define those two terms now. So if this mapping there from X to Y, okay, is said to be one-to-one if the following condition is satisfied, okay? So we can say then R is said to be one-to-one, okay? R is said to be one-to-one if the following condition is met, okay? If I have the coordinates X, Y, and I have another coordinate X, Z, okay, that are members of this relation R, okay, such that Y is actually equals to Z, okay? So this will be the definition of what a one-to-one relation is, okay? So in simple terms, we are saying in this relation R, we cannot find two coordinates that have the same X coordinate or the same first coordinate there, but different second coordinates. We can't find those coordinates, okay? So a one-to-one relation demands that if I have the same first coordinate, even the second coordinates there should be the same, okay? So if I have X, Y, and another coordinate X, Z, then for this relation to be one-to-one, we demand that the Y should be equal to the X, okay? So this is the definition of a one-to-one. And then we try to define what an onto relation is, okay? So we can say if I have a relation, okay, which is a mapping from set X to set Y, okay, then that relation is called an onto relation if the following condition is satisfied, okay? So you can say then R, okay, so then R is said, okay, and R is said to be R is said to be onto, okay, if for any Y that you get in this relation R, okay, so you can say for any element Y that is a member of the set Y in that relation, okay, there exists, okay, so you can say there exists, okay, so there exists an X, okay, so another element X in the set X, okay, such that for all the coordinates X, Y, you will also find them in the relation what? R. Okay, so that's the definition there of an onto relation. Okay, so if the relation R is an onto relation, okay, then you must satisfy these conditions here. So meaning that if you get any Y in the set Y, that Y must have a corresponding X in the set X, such that when you get the point X, Y here, that point should be in that relation. Okay, so in short, every Y should have a pre-image. It should have where it's coming from, okay? It should have an X that is being mapped to it. Okay, so every Y should satisfy that condition. Okay, so these were the first two questions. And then let's move on. So on B now, they're saying prove the following. Okay, the first one, they're saying if R and S are onto relations, okay, then we must prove that their composition is also onto. Okay, and then the second one there, they're saying if R and S are one-to-one relations, then their composition R of S is also one-to-one. Okay, so we are trying to prove that this guy here is onto and this guy here is one-to-one, given that the R and the S, okay, they are onto and one-to-one respectively. Okay, so you That's the thing about real analysis. Okay, so you have to know the definition, and then you have to know how to apply it. Okay, so since we know what an onto relation is, okay, it won't be difficult for us to show that the composition is also onto. Or since we know that the definition of the one-to-one relation, it won't be difficult for us to show that the composition is also one-to-one, because we are going to use those same concepts that we have in the definition for us to show this proof and that proof. Okay, so let's start. So B1. So B, okay, so we start B here. So B, this is B1, okay. So B1, we have been given that the relation S, okay. Okay, so we've been given the relation S and the relation R, okay, that these two are actually onto. And then we want to prove that their composition, which is R of S, I mean, is also onto. Is also onto. Okay, so what do you think we should do? Okay, so for your proof to be easier, you should establish mappings. You should say maybe the relation R maps this to this, and then the S maps this to this. Okay, so for this proof, let's choose our relation S to be a mapping from X to Y. Okay, and then our R to be actually a mapping from Y to Z. Okay. Okay, so if these are my two mappings, and I want to show that R of S there is onto, okay, then if I take their composition, okay, so if here I have a coordinate X, Y, and then here I have a coordinate Y, Z, okay, and I take the composition R of S, we know that you have to start with the second, the relation that is there, right? Okay, so if I start with my S, I see that my S maps X to Y, okay, and where does the relation R map the Y to? Okay, we see that the relation R, okay, maps the Y to the Z, okay, so meaning this relation R of S will just map the X to the Z, okay, so we actually want to show that this relation X, comma Z, okay, not Y, we want to show that X, comma Z there is actually a member, okay, it's actually a member of this composite function, which is R of S, okay, so this is the point where we are driving to. Okay, so let's begin the proof now. Okay, let's begin the proof. So we are going to say that okay, suppose we will start with a claim. So we're going to say suppose, okay, that R and S, okay, suppose that R and S are actually onto relations. Okay, so if R and S are onto relations, then by definition we know that the following is going to be true. Okay, so if I say let an arbitrary element Z be a member of the set Z, and we know that this set Z is present in which relation? Okay, we said it was present in this R there, according to what we chose our mappings to be. Okay, so since the set R is actually onto, okay, then by definition we know that. Okay, so you can write that since R is onto, okay, so since R is onto, then by definition there exists, okay, so there exists a Y in the set Y, okay, such that have the coordinate X, comma Z, okay, has been a member of my relation R. Okay, so this is what I have there. And then from there, I can also get an arbitrary element, which will be in set Y. And we know that Y is in both the relation R and S, right? Okay, so I can say let an arbitrary element Y be a member of set Y. Okay, then since my relation S is onto, okay, then by definition we can say that then or there exists, okay, there exists an X in the set X, okay, so we can say there exists an X which will be in the set X, okay, such that X, comma Y will actually be what? Will actually be a member of this relation S. Okay. So from there now we can even see the answer there. It's shaping up. Okay. So remember we wanted to find the relation R of S. And if we're finding R of S, it means we are starting with the coordinate that we have in S, right? Okay. So here you can clearly see that if I have x comma y in x comma y in S, okay, and then this same if x is mapped to the y in S, what does this y map to in the R? Okay, so we can see that if x is mapped to the y in S, this y is mapped to the z in R. Okay, so we can therefore conclude that therefore I have the coordinate x comma z being actually a member of my R of S. Okay, and then we have achieved this x comma z in this relation. Okay, and then you can actually conclude now. So you can finally say that since the z was an arbitrary element, okay, was an arbitrary element, since z was an arbitrary, okay, since z was an arbitrary element of the set z, and also, okay, and also since y was an arbitrary element of y, okay, okay, so since y was an arbitrary element of the set y, and you can say of y here, okay, then it means that actually the R of S is onto, okay, R of S is onto, because for every Z that we can get here, we'll always find a pre-image, which is the X, okay? So this is actually how you conclude. So you say if Z was an arbitrary element of set Z and Y was an arbitrary element of the set Y, then R of S is actually onto, okay? It's actually onto. Okay, so that's how you solve the first one. And then we go to B2, okay? So B2 here, we're just proving that if two functions are one-to-one, then even their composition will also be one-to-one. So if R, okay, and S are one-to-one, are one-to-one, then we must prove that what? Okay, we must prove that R of S is also one-to-one. It's also one-to-one. Okay, so we know the definition of the one-to-one relation. Okay, no first coordinates should have different second coordinates. That's how we defined it, right? Okay, so we're actually going to use that same principle. Okay, we're actually going to use that same principle. Okay, so we'll start by the proof, always by claiming. Okay, so we can say suppose that my R and my S are one-to-one. Okay, so that will be your claim there. Suppose that my R and S are one-to-one, and then you can let the foreign coordinates be a part of this composition here, and then our main focus will just be to prove that the second coordinates are actually equal to each other. Okay, so you can say let we can say x comma z1 comma x comma z2, okay, x comma z2 be a member of this relation here. Okay, so be a member of R of S. Okay, so what we want to prove actually here is that this z1 is equal to the z2. Okay, so if we can prove that, then our proof will be done. That's all that we have to prove. Okay, so now remember that okay, so remember that this relation R was from what to what? Okay, was from we said the R was from Y to Z, then the S was X to Y, right? So remember that. Okay, so we can say suppose that I have these two elements that are present in the relation R. Okay, so suppose that I have Y1 comma Y2 that are members of the relation R. Okay, such that if I get an X and then I relate it with the Y1, and I get an X again and I relate it with the Y2, okay, such that these coordinates here will be a member of this relation R. Okay, then here we said suppose that R was a one-to-one. Okay, so by definition, if R is 1 to 1 and we have coordinates x, y1, x, y2 that are part of this R, okay, then you can say since the R is 1 to 1, okay, so since R is 1 to 1, okay, since R is 1 to 1, then we know that y1 will actually be equals to what? Y2, okay, so that's the first thing that we've shown there. We've shown that y1 is actually equals to y2. But remember, our main aim is to show that z1 and z2 are equal. Okay, so from here, what can you do? From here, what can you do? We can actually combine each of these y values with those x value, with those z values that we have. Okay, so we can say that combining each y value with the z value, combining each y, okay, with each z, okay, we get that we have the coordinate. If I combine my my y1 and my y2 with the z1, okay, I'll have y1, comma, z1, okay. So this actually should be equals to, when I get my y1 again and I combine it with my y2, okay. And then we can also combine y2 with them. So we say y2, comma, z1, or is actually equals to, you can put your y2 there, then comma, z2 there. Okay, so from this, we can see that this pair of coordinates is just equals to that, and this pair of coordinates is actually equals to that. Okay. Okay, so from here, we go back to what we supposed here. Since we said, where is it? We said that S is 1 to 1. Okay, so it means that here you can say since the S is 1 to 1. Okay, since the S is 1 to 1, we actually get that the Z1 will actually be equals to what? To the Z2. That's what we get here. So here we first showed that y1 was equal to the y2, and then we combine each of these y values with the z value, the z value that we have here, okay, z1 and z2. Okay, so if we combine them with that, okay, and we conclude that since S is 1 to 1, it actually means that this z1 is actually equals to the z2. Okay, or just from here, you can see that for this y1 z1 to be equal to the y1 z2, then this coordinate here should be equal, right? Even this one here it shows. Okay, so now since we've proved that the z1 is actually equal to the z2, then we can actually conclude that means our R of S is also 1 to 1. It's also 1 to 1. Okay, so maybe it can be a bit complicated, okay, but just try to pass through. If it doesn't make sense, you can always master. Okay? You can just master the proof, because Muzundu will never bring anything that is outside what you cover in class and what he brings in the class. Okay, so this is the proof, and then we can actually go to the other question. Okay, so the other question now is 3. So let's try to read 3 and actually understand it. Okay, so 3, what does it say? Okay, so let's continue. So we are on question 3 now. Let's read the question and understand it. Okay, so they're saying if we have a relation at R that maps X to Y, okay, and this relation is onto and injective, such that the domain of that relation R is the whole set X, okay, then we must prove that there exists an onto and injective relation S, which maps Y to X, okay, such that the composition S of R is the identity on X, and the composition R of S is an identity of Y. Okay, so from this question, before you even start to prove it, okay, you must understand, okay, what the question is saying. Okay, so here they're saying if a relation R that maps X to Y is onto and injective, and the domain of the R is just the whole set X, then we must prove that there exists an onto and injective relation S, which maps Y to X, such that the composition of S of R is the whole set, is the identity on X, and then the composition R of S is the identity on Y. Okay, so what this means is that, if I can roughly explain it. Okay, so let's come here. So they're saying the relation R is from Z to what? To Y. And then the relation S is from Y to X. Okay, so it means in this relation, we are going to have the coordinates of the type X comma what? Y. And then in this relation, we are going to have the coordinates of the type Y comma what? X. This is what it means. Okay, so meaning that if I want to find my S of R, okay, if I want to find my S of R here, I want to find out what coordinates are in the S of R. What do I do? Okay, so we know that when you're finding the composition, you start with the second relation there. So what is the coordinate in R? The coordinate in R is X is mapped to Y. And then that Y is mapped back to X, with this relation S. So in this relation here, we're just going to have the coordinates X, comma, X. Okay, so this is what they mean an identity on X. Meaning when we find R of S, we're just going to be finding X, comma, X. And then if I have R of S, it means my coordinates will be in what form? Now we're starting from the S. So Y is mapped to the X, and then this Y is mapped back to the Y in the R. Okay, so the composition R of S will just be in the form Y, comma Y. And this is what they mean by the identity on Y. Okay, so this relation X, according to this equation here, we must prove 4 things. Okay, so the first thing that we must prove is that S, okay, the first thing that we must prove is that S is injective. Okay, so injective simply means it's a 1-to-1 relation. Okay, so this is the first thing that we must do. And then number 2, we must show that S is onto. Okay, then 3, we must show that the composition of SR is just actually the identity on X. And then number 4, we must prove that the composition of R of S, okay, is actually the identity on Y. So this is all that we want to prove. We must prove that S is injective, S is onto, the composition S of R is just the identity of X, and the composition R of S is just the identity on what? On Y. Okay. So these first 2 are very simple because we know the definition of a one-to-one, we know the definition of an onto. So it won't be that difficult, right? Okay, so let's prove. So in this proof, we take advantage of what we have already been given, which is that this Y here is actually onto, and it's also one-to-one. So we'll take advantage of that to prove the rest. Okay, so let's start by proving that S is injective. Okay, so to show that S is injective, we can say let. Okay, so before I start, let me just write what we're doing. Okay, so here we show that S is injective. Okay, so we are showing that S is injective as our first objective. Remember, we have 4 objectives, right? Okay, so we can say let Y, comma X, comma X, comma Z, comma Y, comma Z, be a member of this relation S. Okay, so if if Y, comma X and Y, comma Z are a member of S, okay, then it means that, okay, so here you can write such that, okay, such that I have X, comma Y and Z, comma Y being a member of R. Okay, so this is what I have there. And then also let, so you let in both directions. So also let this thing here to be a member of S. Okay, also let X, comma Y, X, comma Y, and then Z, comma Y be a member of S. Okay, such that then we get the opposite, which is Y, comma X. Okay, so you can see I'm just flipping these coordinates, right? So Y, comma X, and then I have Y, comma Z is actually in R. Okay, then from here we can take advantage of the fact that the R is already injective. Okay, so we can say that since R is injective, Then what does that mean? Okay, so if R is injective, then it means that my X will actually be equal to the Z. Okay, my X will actually be equal to the Z. And if my X is actually equal to the Z, it means the first coordinate here are the same, which is y, and even this X is equal to the Z there. So that satisfies the definition of the one-to-one. Okay, so if X is actually equal to the Z, okay, then it just actually means that the S is injective. So you can say, therefore, S is injective. Okay, so this is our first objective. We have proved that S is injective. Then now we prove that S is onto as our second objective. Okay, so our second objective, we prove that S is actually onto. Okay, so this is very simple. Again, we take the advantage that R is already onto. Okay, so what are we going to say? Okay, so to prove that S is onto, we're going to say that we need to show. Okay, we need to show that for any X in the set X, there exists a Y. There exists, okay, so there exists a Y in the set Y such that X, Y is actually a member of what? Okay, such that, here I started with the X and then the Y. So meaning this coordinate here should be X, it should be Y, X. Okay, so for any X in X, there exists a Y in Y, such that Y, X is actually a member of the relation S. Okay, and then we can also let what we know now. Okay, we can also say let X, Y, X, Y here. Okay, so this is X, Y, be a member of R, what we know already. Okay, so let X, Y be a member of Y. Then this will actually mean that what? To actually mean that this, what we have here, the Y, X will just be a member of the S. Okay, so if X, Y is a member of R, then it means Y, X is a member of what? Of S. Okay, now we can say since R, okay, now since R is onto, okay, since R is onto, we can actually say that. Okay, so since R is onto, we can actually say that for every X in X, there exists. Okay, so there exists a Y in the set Y. Okay, a Y in the set Y such that X, Y is actually a member of what? Of this relation, R. Okay, and then from here, so here we are using this one here. So we let X, Y be a member of R. Okay, and then we're saying for every X there exists a Y such that X, Y is a member of this R. Okay, so we can also do the same for this guy here. So Y, X is a member of S. We can say for every Y there exists an X. Okay, so we can actually say that this means that for every, okay, so for every Y in the set Y, there exists, okay, so there exists an X in the set X such that, okay, that the coordinates Y, X is actually a member of S. So this actually proves that hence the S is onto. So it's just playing around with the definition. So hence S is onto. Okay. So we have achieved our second objective, which is proving that S is onto. So now the third one is we want to show that S of R. Okay, so this is the third one. So we want to show that S of R is actually just a relation, an identity relation on what? On X. So we want to show that all pairs that you can find in this S of R, okay, they will just be mapped from X and then they're going to X. So let's do that. Okay, so to show this, okay, we'll use that part of the domain, this part here. If I go back to the equation, this part here. It's very important to prove that part. Okay, so we know that the domain of the relation R is the offset X, right? Okay, so if I come here, I'm going to say that since we know, okay, since we know that that the domain of the relation R is just the actual or the offset of X, okay, then it means that, okay, so then it means the domain of this relation here, the S of R there, will just also be X, okay? So why are we saying so? Because we know that if we're getting points here, we'll first get a point from the R, and we know that the domain of this R, meaning all the coordinates that we can get for this R here are coming from X, right? Okay, because the domain of R is S, so they're coming from S, meaning even the domain of this S of R will just actually be what? The set X. Okay, it will be the set X. Okay. Okay, and then we can take advantage of the property where they say the S, the R is an onto and it's also one-to-one. Okay, it's injective and it's onto. So we can say we can have, okay, so we can have a coordinate X, Y comma X, I mean, being a member of this relation S only if, okay, or if and only if, okay, so if and only if, this is how we write it, okay, if and only if X comma Y is actually a member of what? Of R. Because remember, the R is a mapping from X to Y, and then S is a mapping from Y to X. So if I have a coordinate there, X comma Y, it means there exists, or this coordinate X comma Y will only exist, okay, if and only if we have X comma Y, which is a present in this relation R there. Okay, and then this actually says that what? Okay, this actually shows us the image of this function here, the S of R. Okay, so it shows us that the image of S of R is just actually the same set X. Okay, so the domain of S of R is X, even its image is X. So you can see that the mapping just be from X to X, right? Okay, so now we can let an arbitrary coordinate be a member of S of R. So now you can say okay, you can say Y comma X. Okay, so let Y comma X actually be a member of the relation S of R. Then what would this mean? Okay, what would this mean? Okay, it would mean that there exists a Z in the set Z, okay, such that, okay, there will be a Z in the set Z such that I can only have Y comma Z in this relation S if and only if I have a Z comma Y in the relation what? R. Okay, so whatever is present in the R, the opposite of it should be present in the S. So if I have a coordinate like this in S, it means I should have that coordinate in the R. Okay, and then from this we see that if we get the composition, okay, if we get composition, which is S of R, okay. Okay, so if we get the composition S of R from these two coordinates here, we'll start from S. Okay, so if Y comma Z is a member of S, okay, and then Z comma Y is a member of R, okay, it means the relation R of S of R, we're starting with the R, right? Okay, so if I start from this R, I can say that the Z is mapped to the Y, and then this Y is mapped to back to the Z in the S, right? Okay, so we can conclude that from there we have a Z comma Z, which will be a member of S of R. Okay, and then we can say since the y comma x that we let where is it that we let here. Okay, since the y comma x that we let there was arbitrary, so since the y comma x was arbitrary, okay, since the y comma x was arbitrary, it follows that it was an arbitrary element of this S of R. It follows that the composition S of R is just actually X being mapped to X, okay? Because all the coordinates that you'll be finding here will just be the same, okay? Will just be the same. So the X will be mapped to the X. So that's how you prove that. And then we also have to show that the fourth objective, we also have to show that R of S is just an identity on the Y. Okay, so whatever we did here, we just do the same for the other one, which we'll just be doing the opposite, right? Okay, so the fourth objective there, we're trying to prove that R of S is actually an identity on Y. So meaning all the coordinates that we are going to find here will be of the form Y comma Y. This is what we want to show. Okay, so we can use the same approach. Okay, we can use the same approach. Okay, so if I go back to the question here, they are saying the domain of R was just the whole set X. So this means that the domain of this S here is just the whole set of Y. Okay, because R is the whole set of X, S is the whole set of Y. So we can just actually do the opposite of whatever we are doing here. Okay, so let's do that. So we are going to say, okay, so we can start. We can say we know that. Okay, so that we know that the domain of S will actually be the set Y. Okay, so meaning even the domain of R of S will just be the set Y because the first coordinate will be coming from X. Okay, so we know that the domain of S will just be the set Y. Okay, therefore, or you can say thus, the domain of this R of S will actually be this same set Y. Okay, and then from there, we can let, okay, so let X comma Y, okay, be a member of R. Okay, so this can be true if and only if, okay, if and only if Y comma X is a member of what? S. So you can see it's just the opposite we are doing, right? Okay, so therefore this shows that the image of, okay, the image of R of A, okay, the image of R of R of S will actually be the whole set Y. Okay, so you can see the domain is Y, the image is also Y. So we only have Y comma Y present in this image. Okay, so to proceed, we can say now let an arbitrary coordinate X comma Y be a member of what? Be a member of R comma X. R of S, I mean. Okay, then there exists. Okay, then there exists a Z in the set Z. Okay, so a Z in the set Z such that the coordinate X comma Z can be a member of this relation R if and only if the coordinate Z comma X is also in the set X S. Okay, so that's what we get there. Okay, and so from this we know that Z comma Z will be in the composition. Okay, so Z comma Z will actually be a member of the composition R of S, and we can see it from here. Okay, so if I start from Z, from S here, Z is mapped to X, and then this same Z here, I mean this same X here is mapped back to the Z. Okay, so meaning Z comma Z is actually a member of R of S. Okay, it's actually a member of R of Z. Okay, and then from here we can actually conclude that since this coordinate here that we chose was arbitrary, okay, this one here. So since the X comma Y was arbitrary, since the X comma Y was arbitrary, okay, we get that, okay, we can say it follows that R of S is actually the identity on y, because all the coordinates will just be y comma y, y comma y. Okay, so we've proved all the four. Okay, we've proved all the four. It means we are done with our question. We proved that S is injective. We've proved that it's onto. We've proved that derivation or the composition S of R is just an image on X, and we've also proved that R of X of S is just an image on Y. So it means we have answered this question here. We have answered this question. Okay. All right. So now we go to the C. We go to C, and then we see what we can do with it. Okay. So C, they're saying consider the relation R defined. Okay. Consider the relation R defined by what we have here. Okay. So defined by, we have a coordinate X comma Y such that X squared is equals to Y squared. Okay. Given that X and Y are both real numbers. Okay. They're both real numbers. Okay, so we are considering that equation, and then the first question there is sketch the relation. So we just want to sketch the relation. So the relation here is represented by this formula here, which is y squared is equals to x squared, or x squared is equals to y squared. Okay, so how do you sketch this? So this is very simple to sketch. So if this is C, right? So C1, we have the relation where we have the formula y squared is actually equals to x squared there. Okay, so how can you sketch that? How can you sketch that? Okay, so we can actually take the root for both sides. So if I take the square root of x squared, and even here I take the square root of y squared, okay, it means that what here our plus or minus x is equals to, even there our plus or minus y. Okay, so it means if I get the positive x here and combine it with the positive y and the negative y, our y, I mean our x is equals to what? Y, the first one, and then the other one will be x is equals to what? Minus y. Okay, and then if I get the negative x, to have negative x is equals to y, and then the other one will be negative x is equals to what? Minus y. Okay, so what you get from this is actually that minus x is equals to minus x is just the same as x is equals to x, right? And then x is equals to minus y is the same as minus x is equals to y. Okay, so these two here are the same, even those two are the same. So what you actually have is just that x is equals to plus or minus y. Okay, this is the relation that you have. So you can say that this is the first one, and then you have the second one there. Okay, and then we just want to plot this line. So we want to plot this line, and again we want to plot this line. And we see that these are not something, this is not something that is difficult, right? We can actually plot it. Okay, so if I write my equation here, x is equals to y, then the other one I say x is equals to minus y. And then I can plot this on my xy plane. Okay, so this is my 0, then I'll say this is my x, this is my y. Okay, so what is the line x is equals to y? It's just this line here that passes here. Okay, and then what is the line x is equals to minus y? It's just this line here. Okay, so this will be our graph. So this will be the line x is actually equals to y. Then this will be the graph where we say x will actually be equals to minus x. So we have sketched the graph. Okay, we have sketched the graph. And then the other question is what there? They're saying find R of S. Okay, where S, okay, where S is given by this relation here. Okay, so now we have two relations. We have for R, and then we have for S, and then we are finding their composition. Okay. So this might look it might look difficult, but it's actually very simple. Okay, it's the same as they give you. If I would use first year concepts. Okay, it's the same as they give you two functions, and then they want you to find the composition of those functions. Can you feel? You can't. Okay, so if for example I have f of x, maybe they say this is 2x. Okay, and then they give me g of x is I would say g of x is let's say 4. Okay, and then they ask me to find f of g. Can you fail to find f of g? This is exactly what we are doing here. We're just finding r of s. So this is the formula for s, then this is the formula for r. So if I find my f of g here, I'll just write 2x, and then wherever there's x, I'm going to represent the function g. Okay, and this will just be 8. So we'll use this basic information here. Okay, so I have my relation r, which has this formula. So I'll say r, I can say of what? Okay. Okay. Okay, so I would say R of Y is actually equals to, what was that formula that we are given there for the R? Let's check. We had X squared, Y squared, okay? And then we reduce this X squared is equals to Y squared. We reduced it to what? Okay, so before I write this, maybe I can confuse some people. So let me say this, okay? We had X comma, or X squared is equals to Y squared, right? Then we said we can take the root of both of these, and this formula will just become X is equals to plus or minus what? Y. That's what we said, right? So this one here will be our R. And then our S, what is the formula for our S? We had the X is equals to, let's check, Y squared, okay? Y squared, okay? So actually we can get this as the relation of X, which will just be equals to plus or minus Y. And then this will be the relation of, that will be the relation of R, this will be the relation of X. Okay, so I'll say the relation of R of X, because I'm starting with the X there, right? So I'm going to say R of X, X if not in. So R of S is just equals to plus or minus what? Y. And then S of X is actually equals to what? Y cubed, like that. Okay, and then I want to find the relation R of S. Okay, meaning that I can actually write plus or minus. Okay, so this is the relation for R. And then in this R, I'm going to substitute, okay, I'm going to substitute this Y here with the function for the what? Not the function, but the relation for the S. Okay, so the relation for the X, wherever there's Y, we just have to put Y cubed. Okay, so this will be actually the S of R. Then you can represent it in terms of the mapping. So you'd say X comma Y such that X is equals to this formula here, plus or minus Y, the third power, okay, such that X comma Y is actually a member of this relation R. Okay, and then you put that. So this will be a relation here. Okay, so that's that. And then we can do question 3. Okay, we can do question 3.